little bit briefly on crystallography and substitution of manganese with nickel before we move on to diffusion and ion conduction. Because of course it's all related and it builds up off, the subjects build up and off of each other. So last time, right, we left off at how electrochemistry is affected by the crystal structure and if there's a phase transformation. In this particular system, lithium manganese oxide, that there can be a two-phase coexistence between the cubic phase and the tetragonal phase, and that manganese dissolution is an issue because of the instability of manganese 3+ in the tetragonal tetragonal crystal structure. So it's the phase transformation itself, really limits the use of this material to, if you wanted to stop this phase transformation and not experience, volumetric changes, which would be deleterious to, to your electrode once you fabricated it, right? Once you made the composite. So the crystal structure informs us of the electrochemistry, which voltage window we can operate within, what the resulting capacity that's going to come out of that. And where we left off is how to then mitigate this challenge that is inherent in the lithium manganese oxide crystal structure and its use as a cathode material. And so we talked about, well, if manganese, dissolution is a problem, then, but the higher voltage is something that we want to keep, then we can substitute in with nickel to reduce the manganese 3 concentration in the spinel structure. So that's great, and it does mitigate that issue somewhat. And so we left off as the emergence of cathode materials such as NMC, right? With replacement of not only cobalt, manganese, but the inclusion of nickel stabilizes the cathode material itself. And so resultingly, of course, when you add in nickel, you also get increased voltage. So that is an advantage. Now, what I haven't talked about, because I've only corralled our discussion so far around the chemistry and the crystal structure and phase stability, I haven't talked anything about thermal stability, right? So with nickel, if you've worked with materials like NMC, right, then the higher nickel content is and has been and continues to be a challenge, right? Increasing nickel, like, so here in this particular composition, right, if nickel, manganese, and cobalt are all the same stoichiometry, we call that the 1-1-1, right? Third, 1-1-1 would be the colloquial, vernacular. But when you increase nickel to something like 622, 811, those are the ratios of nickel to manganese to cobalt, then we start to really have issues with phase stability because nickel at high temperatures, it's not stable, right? So then you kind of have to balance. All right, I have to balance manganese dissolution, but I also want higher thermal stability. So there's a balance. So that's what people have been trying to do, right? People have been actively trying to engineer compositions as well as morphologies and microstructure so that you come up with a balance where you get sort of the best of both worlds, right? Either you make some complex morphologies like a core shell type structure with different compositions. Maybe you tune the particle size so that you increase diffusion and you stabilize the surface area so it's not too small, not too big. So there are countless strategies to try to stabilize this composition where you increase the nickel content, so nickel-rich cathode material, right? So far where we're at is we talked about the thermodynamics, we talked about the crystal structure, we talked about chemistry that affects the stability of these materials and their usefulness as cathode materials. So the next topic we're going to talk about is diffusion. Okay, so you make a material, is it going to be useful at high cycling rates? Are the ions going to diffuse at a rate that is useful? And the ions being, in particular, lithium ions in both cathode materials, anode materials, as well as solid electrolytes. So if you take a look at our schedule, once we're done with the foundation, sort of the theory of ion conduction, and then also the theory of electrochemical methods, a summary, not the entire BARD book, right? That's a whole semester that Professor Ancook teaches. Then we can start to discuss each material as a whole, as opposed to piecemeal example like you see here. We can really take a look at state-of-the-art materials and understand why they've been engineered to the composition that they are, and also the morphologies, the microstructure that people have been working on to get to get us to where we are. Okay. So so any questions before we move on? Or comments? Yeah.
Like B subscript I.
Okay.
Equal to another number. I just wanted to make sure that it's just the distance.
Oh, yes. So in that reference, I think I stated it there, but if my memory doesn't serve me well, you're talking about this one. Yeah. It is the distance. It is the van der Waals layer. Now, there can be a little bit of expansion due to deformation once the intercoolant comes in, or if there is, an intercoolant next to another intercoolant or things like that. But yeah, that's basically the van der Waals layer.
And for both B and I.
You're talking about D sub I.
D sub I sub C.
Right, so I sub C is the number of layers. So for each stage, you can see that the big I gets smaller and smaller. Whereas the sub I is just a bit when there's an intercoolant. But in this, I see. Okay, so this graphic was modified from, okay, so the citation should be here, but I can note, yeah, I can note that the paper is in the directory, and I can put that in the discussion forum what the exact equation is in the paper. But that is a good question, because it does lead us to the ion conduction part and how we think about diffusion as it relates to ion conduction, particularly in regards to, let's say, the crystal structure and defects. Because then we start to sort of inch towards real materials. But even though I should preface the discussion of atomic diffusion, the diffusion within the microstructure does not always explain what you see or measure in terms of the apparent diffusion. And this is where the transference number comes in, and this is where the Haven ratio comes in. But understanding how ions diffuse in a solid will help us understand, for the most part, what's happening macroscopically. Okay. Oh, but of course, just can't handle all the crystal structure. All right, so this is, I'm hoping to cap this, well, in about a lecture and a half. So we have time to talk about electrochemical methods, but no rush. Okay, so the next part, right, is pretty important because we do throw around terms like ionic diffusion, you know, especially as we discuss all solid state batteries, which are quite prevalent these days, right? It's a hot topic of research. So this is something that we really want to drill down and understand the fundamentals. So I'll be focusing on, you know, ion conduction in conventional lithium ion battery, cathode materials. I'll touch upon solid electrolytes as well, but we'll be discussing, you know, like LGPS in great detail as sort of like a archetypical material for solid electrolyte. But the takeaway from today's discussion will be, you know, the different diffusion mechanisms that happen in the solid. Also, how do we think about activation energies, particularly as it pertains to single crystals, perfect crystals, and also defects. And then the Haven ratio, where, you know, macroscopic ion conductivity and diffusion that you can get from ion conductivity is not always, does not always line up with what you would expect microscopically, right? Okay, so we go back to Fick's. Fick's first law. You know, why do ions move? You know, why are they motivated to move at all? Right? Well, we hook them up to and apply a voltage, so there's a bias of sort, right? So there's a chemical gradient. Typically, one side doesn't have lithium ions, the other side does, right? So we're motivating the move of these ions. We can apply electric field. We can basically move. But Fick's first law, you know, as long as there's some driving force, let's say there's a concentration gradient, right? Higher concentration on one side, lower concentration on the other side, there will be some sort of flux. And that flux is just directly related to dCdx. So the change in concentration as a function of distance, x. Here, this is the simple 1D case, but of course you can generalize that to dCdy times dCdz, right? So pretty standard so far. But that gives us the relationship of the diffusion coefficient for that particular element that we're interested in, or the particular ion that we're interested in. And the diffusion coefficient is just also the diffusivity, one and the same. And so we have different species. Typically, we think of lithium ion as the only species that's moving. That's not always true, especially if you start to mix in, you know, if you add in defect sites by substitution, the substituting ion can also move. Your anion could also migrate. Now, in the typical cases that we think about, right, the anion is much larger, it's not as mobile. So here we don't really have to worry ourselves with the subscript I, but more fundamentally, we should. You know, it's not always the case that lithium is the only species that is moving. But in the examples that we'll talk about today, it is. So we can treat it as the only species. Because otherwise you have to take into account all the fluxes left, right? And then the difference will give you the overall flux. Okay, but so that's a simple case. Of course, concentration gradients aren't always steady state, right? That they change over time. So, one moment. I know this hasn't been updated. Okay. Well, team, there are some things that haven't been updated. So one moment. Okay, so it says it's updated, but that doesn't appear to be the case. If you look on your, try to be a little bit more specific, a little bit more detailed. So despite it saying that this has been updated, I can tell you it's not. Well, that's okay. I will verbalize the changes for you. Okay. So, right here. So for Fick's second law, which is what we're really interested in because that's more our reality, right? Is that at a certain distance x now, we have the steady state concentration C sub s and a starting concentration C naught. Over time, right, at t equals 0, you have, your concentration like so, but over time, the concentration changes. So the solution to this, to Fick's second law, which tells us how the concentration at a distance x and also at a certain time is related to the diffusivity, right, in the time. So you probably have already derived this, in your classes, in terms of getting the solution, but we can, and you can look up, the numerical solution using the error function. But that's just all to say at a certain distance x, we can look up the error function and we can get what the concentration C sub x is at a certain time if we know what the steady state concentration will be. But that's all to say the diffusion length L is proportional to the diffusivity times the time. Now, these two things are important because, right, if you want high rate capability, right, then you need diffusivity to be a high value, right? Alternatively, you could also just decrease your diffusion length to increase rate capability of a material as well, right? And so those are the strategies that people have employed to engineer high performing cathode materials. Okay. Now, in terms of the lithium ion migrating through the solid, there are a number of ways that the lithium ion can migrate, right? So in general, we think about the random walk, right? If the lithium ion can basically move as it pleases, then it will do so. If it's a vacancy mediated mechanism, right, what that's telling us is that there are vacancies, and if it's a Schottky disorder, that means that there's a pair of cation and anion vacancies together. And so there can be a hopping mechanism where the lithium ions can, occupy these vacancies. And so that's a vacancy mediated mechanism. And so we're interested in these defect mediated diffusion mechanisms, whether it be vacancy or interstitials, because those are going to be the dominant mechanisms that you'll see in these types of materials. Now there's more, like there's interstitial, and there's knockoff, there's radiation damage, diffusion, all of that. That's a little bit less pertinent for us. Not really sure why it's verifying Outlook. So there are Schottky disorder. The lithium ions will move through a vacancy mediated diffusion. Now, this tends to have lower lower ion conductivity and higher activation energy. Now, that's because you need an extra energy to form, right? You need to form the vacancy. So, and as you break these bonds and the vacancies also move, you have this extra energy term that's going to increase your activation energy. In contrast, you can also have ions move through the interstitial sites. So that can lie in between the crystallographic sites. But of course, the criterion would be that the ion that's moving needs to fit within those interstitial sites, right? So you're going to need something that's small. Now, lithium ions, of course, are quite small. We've discussed that, a number of times now, and we've looked it up. And in fact, when we looked up, the +1 charge with a coordination number of 6, we said that's 0.76 angstroms. Of course, it can be smaller as well, 0.59 angstrom. So it's one of the smallest ions, right? But it's still quite large relative to electrons, right? Electrons have a radius of 10 to the minus 22 meters. So immensely much smaller. So when we talk about mass transport, right, we're inherently dealing with diffusion mechanisms that is just going to be so much slower than what you expect in terms of, relative to, say, electronic conductivity, right? So in terms of Frenkel disorders, right, you have a pair where you have a vacancy, but then the cation that was once here has moved there. So now you can imagine that there's going to be some repulsions as well, because the charges are now very close together, right? And so this type of disorder also motivates how lithium ions move within a lattice, where it's going to try to avoid some of these defects, interestingly enough. And depending on the crystal symmetry, this can be advantageous, but this can also be, disadvantageous, depending on how you engineer the material. So this is particularly the case for lithium iron phosphate, right? One of the most well-studied cathode materials, on highly commercializable cathode material, and the fact that it has 1D transport, defects really play a role in the ionic diffusion of lithium within the crystal structure. Okay, so as I mentioned, the number of diffusion mechanisms are plenty, and they all have their quirks, their advantages, their disadvantages. So when we talk about interstitial movement of lithium ions, we're really talking about the direct. We're really talking about, we're talking about direct interstitial movement mechanism. But that's not the only one, right? There is this type of movement, it's called a ring interstitial. There's also direct exchange, and there are plenty of examples out there for each particular material that's been studied, how lithium ions move within each type of material. But we're going to focus on the more dominant one, which is the direct interstitial migration. And that's what we're going to focus in terms of the derivation for diffusion as it relates to ionic conductivity. But I provide this reference here in case you want to study and look into all these other types of materials. Okay, so in terms of the ionic conductivity and how does it relate to diffusion, we start off with statistical mechanics. So each ion is just rattling in its crystallographic site, right? And at some point, at some energy, there's always, some entropy, right? This atom is going to have enough energy statistically to migrate. So what that energy is this delta G. Okay. So if it can overcome this delta G, and you can simply do that by just raising the temperature, right? There will be some net velocity that's dependent on all these parameters, right? And these parameters, we'll just lump them all into one nice prefactor at the end, but this is what they are so far, right? There's going to be some attempt frequency nu. Z and E can be lumped together as a charge, but Z is just the charge times the elemental charge. So Z times E is just Q, which is probably something you're more familiar in terms of seeing. The A naught is the jump site. So now this depends on the crystal structure. It also depends on the crystallographic direction in which the ion is jumping. So, you know, in lithium iron phosphate, right, it's a 1D tunnel structure. So if it's going along the fast ion transport direction, the O10 direction, that jump distance of 3 angstrom is going to be different than jumping in between the channels, which is farther, like 4.5, 5.5 angstrom, right? Depending on which site you land up. So now the crystal structure, you know, comes into play, and then KBT is full point constant times the temperature that you're at. Okay, so what we've done so far is we're just saying this ion can diffuse if it can overcome some delta G, and it can jump that site, or the distance A naught. Okay. So then we also think about its mobility, and you probably have discussed mobility when you talk about semiconductors, you talk about electrical conductivity, you talk about, you know, the ease of these carriers moving through the material. These carriers are now the ions, and so you're concentrating how easy it is for these ions to pass through the matrix. We also think about its mobility. So here we now start to relate the charge, the concentration, and the mobility to the to ionic conductivity, which is something you can measure. And now we basically move everything out to the prefactor, and we come back once again and we say, okay, well, there's still this statistical term where they can overcome this energy, then we can measure it, you know, relate that back to its ionic conductivity. Okay. But more realistically, right, the delta G, you can break into two terms, the enthalpic term and the entropic term. So all I've done so far is move the prefactor. All I've done is move the prefactor from here out to here, and broken up the delta G into the enthalpic term and the entropic term. Okay. All I've done. All right. So then this is where the magic happens. We just say everything in front of the 1 over T is just now the prefactor. We lump that into this sigma naught. And then we say, okay, well, we'll just lump the entropic term into the prefactor as well. And we're going to call it delta naught. Okay. Okay. So now that we have, and we move up 1 over T over here onto the left side, we multiply both sides by T. And so now you have the relationship that's probably more familiar in the journal articles that you've seen, the papers that you've read, right? The sigma ionic conductivity times T is equal to this, you know, energetic term times some prefactor. So we call this delta H the activation energy. Now it's represented by E sub naught that you see in papers. So you can already see, this looks like the Arrhenius relationship that I expect when it comes to ionic conductivity. Okay. So if you take natural log of both sides, you get exactly that. Log of sigma T. So sigma is, now I've taken away the ionic conductivity because I assume we're talking about ionic conductivity. So then you have now the slope, if you plot it over as a log of sigma T as a function of inverse temperature, the slope will directly give you the activation energy divided by the gas constant. Simple enough. Okay, so this is what you can typically get out of looking at these plots. Now, what you've also seen, probably, because I've also seen them, is that you'll see log, natural log of sigma versus inverse T. And so you can mathematically separate them, right? ln of sigma T, you can separate that into ln of sigma plus ln of T. It's all true, but T is variable, right? So the advantage of doing this, while you cannot get the activation energy from plotting ln of sigma versus inverse temperature, it is a useful way of presenting data if you have a lot of different materials that you want to overlay on a plot. You want to see the sigmas relative to each other. It's a very useful way of communicating that information. But what you can't get is just, you can't just pick out the activation energy from the slope. Okay. But that's what you see. So then when you see plots like this, you say, oh, okay, well, over, right, over, some temperature, you could see the ionic conductivity of, either liquid electrolytes that you see here, the more state of the art LLTO, LGPS, perchlorate, even life bonds. You can see, okay, you can compare pretty quickly the different ionic conductivity values to give you a sense of, where your material stands relative to the other materials. Okay, so it is a useful representation. Now you also see, I highlight this figure here because you'll see the inverse temperature here, and that's all fine and dandy, but a lot of times you have to do the mental math in your head. So it's very useful to have T as a, in Celsius in the second x-axis and just convert it for people. So, all right. So so that's ionic conductivity, right? That's something you can measure. It's easiest to measure the ion conductivity and relate that back to diffusivity, right? So you can just measure that, and you could use a number of electrochemical methods, right? You can use electrochemical impedance spectroscopy. You can use titration techniques, potential static, galvanostatic, intermittent titration techniques to get out the diffusion coefficient or the diffusivity. And people have done that, right? So here's just some select papers that have demonstrated these values or measured these values. And so you could see the diffusivity of lithium in lithium cobalt oxide, in lithium manganese oxide, and lithium iron phosphate. And you could see that lithium iron phosphate, the diffusion coefficient is really low, right? So the task now is, how do I increase the diffusivity? How do I increase this value so that I can get this material to perform at a higher rate, so I can discharge and charge quickly, right? Because inherently, just the crystals, the single crystal itself is not going to perform, is not going to be well engineered for fast charging and discharging. Okay. Okay. So the way we relate ion conductivity to that of diffusivity, we go back to our statistical mechanics, and we can relate the diffusivity as it relates to the energy barrier over a distance A0. We remind ourselves the relationship between that energy barrier and mobility. And we use the Nernst-Einstein relationship between mobility and diffusivity. So it's just D is equal to the mobility times kVt divided by the charge of your ion. So then we can plug in these values and say, okay, well, if that's D and that's mu, I can plug in what mu is, and I can get out if I can measure the ionic conductivity, sigma, I can calculate then what the diffusivity is based on that. And I offer both versions here in case you're more familiar with one type of notation over the other. Okay. So the diffusivity will change as a function of the crystal structure, the direction, if you can control, if it's a single crystal and you can control the crystallographic direction that the ions are moving by applying the field a certain way, then so then you can get diffusivity. So then you can also understand then what the different activation energies are for each particular regime, right? So you're going to get different slopes. And if there's a phase transformation, there's going to be an abrupt change in the Arrhenius plot, right? So you can then see all of that and map it out as a function of temperature in your Arrhenius plot. So it's quite powerful to be able to relate microscopically, starting from the crystal structure itself and then building all the way up to something that you can, hook two electrodes together and then just measure what you see macroscopically. Okay. Okay. So in terms of the random walk, what I've alluded to before is that ions don't always move in this, completely perfect random walk, right? There's going to be some correlation because of repulsion of like charges, because of defects within the crystal structure. It's not always going to be the microstructure diffusivity is going to be the apparent diffusivity of the macroscopic material. And so what we can do is we can do some very fundamental studies and put in tracer ions, right? So it can be isotopically labeled, but we can put in these tracer ions and they'll move and they can move. So they don't move with the, let's say, necessarily with the concentration gradient, but what we see is then we can track the tracer ion that's going to follow a random walk model. And the correlation factor is going to tell us the ratio between the tracer ion that moves sort of like in a random walk and what we actually measure. Another discrepancy is that between the, we can also discuss this in terms of the Haven ratio, and that's just the diffusivity of the tracer ion relative to that of basically what you measure. Yes.
So how do you physically tracer ion? How do you implement that into?
So you can isotopically label ions. So you can buy lithium, like lithium 7 rich styrene precursors, and you can synthesize that. Now the chemists, they typically put in, isotopically doped, or sorry, substituted, like 2O, instead of putting in, you put in 2O, or you put in basically another isotope of the element. You take the two ratios. They do that homogeneously, like in a solvent. You could also do it in the solid state. So instead of synthesizing from, let's say, natural abundant lithium fluoride as a starting material, lithium carbonate are the common precursors for lithium metal oxide, phosphate type compounds. You buy lithium, like lithium stuff, that's going to run you about a gram. So it's not inexpensive to do these experiments, but it is possible. Of course, you would have to buy lithium 7 for a neutron diffraction anyway, so you'd be primed and set up for those type of experiments and characterization. Now, another way to increase diffusivity is by engineering your grain size. So how many grains you have, and also the size of your grain and the grain boundaries that are within your material, right? So a grain boundary is just the interface, simply put. There's obviously a lot of mathematics behind this, but and you can get into the really nitty gritty, but for our purposes, we just need to understand that a grain boundary is just at the interface of two crystals. So two single crystals or two grains, right? If we assume that there's within each grain, there's a single crystal. So at the grain boundary, right, there's not only atomic disorder, like when you think of twinning, right, the angles change, but you can also have changes in the crystallographic direction. You can have changes possibly in the crystal structure. If you're looking at the local structure, and there's a formalism for understanding local structure as opposed to the average structure, the composition might change because now there are dangling bonds, right? You have uncompensated charges. So all of these features at the grain boundary affect the diffusivity, right? But the migration energy of the ions in the grain in the boundary is much lower, right? Because there are all these defects that help it along. So that's great, but the concentration of the ion changes at the boundary relative to the distance away from the boundary. So there's been a lot of studies are done. Now, there still can be more. It's not so easy to engineer exactly one type of grain boundary, but that's all to say the diffusivity at the grain boundary is larger than that of the diffusivity within the grain of your crystal because of all of these features that I've just mentioned. And you can get really into nitty gritty of what the Fisher model versus the Whipple model and all of that, but that's all to say diffusivity of grain boundaries is much larger. And so you could get into the nitty gritty of exactly a mathematical and geometric model of exactly where you are from the grain boundary and how that quantitatively affects your diffusivity of the grain boundary. But the takeaway message is if the diffusivity of grain boundaries is larger, then could you think about engineering more grain boundaries, but in a uniform way so that you can have uniform properties from your material then that you can then fabricate into an electrode? And the answer is yes, by the way. Excuse me. Okay. So in terms of engineering ion diffusion, right? Not only do we think about, okay, well, I can change the crystal structure, maybe I can change the morphology. You also can think about the chemistry, right? What type of, do I include in dopants, right? That's a common technique in the semiconductor industry. You want to engineer different electrical conductivity. You have P-type, you have N-type. I mean, you can get down to the ppb level of control in semiconductor, right? And so similarly, you can do so by thinking about changing the doping chemistry to affect the lithium ion diffusion. So that's one strategy. Although you have to be careful, though, there's been a number of studies where, the hypothesis is that if you introduce such a dopant, for increasing electrical conductivity to promote ion conductivity, there have been further studies that have said it's actually not just that increasing electrical conductivity will also enhance ion conductivity. It's that there are other impurities that were not accounted for that actually assisted in increasing ion conductivity. So I say this as, just to say that care really has to be taken to make sure that you isolate, the feature that you're trying to study, because a lot of these things are intertwined, So word of caution out there. When you think, yeah, this, it's so much better. It's not always what you think. It's the cause and effect is not always so apparent. Okay, and that's actually the story of all battery materials, by the way. It's not always obvious. Just because you do something and then you measure something and then you see the effect, that's not always true. And in the battery community, we've seen this time and time and time again, to know that we must do this with great care. Okay, diatribe aside. We talked a little bit about coating materials to prevent dissolution of transition metals, to stabilize, let's say, oxygen loss even, or decomposition at the surface. So you can do that to promote ion diffusion. You can decrease the particle size. So if the diffusion length is related to the diffusivity times time, or the square root of diffusivity times time, we can decrease the diffusion length to increase, right, the diffusion, to the diffusivity. So, and that's what people try to do in terms of nanostructuring materials. Okay. And then crystallinity as well. So if the mechanisms that we've been talking about in solids are crystal, are within crystals, what if you lower the energy landscape altogether and make your material amorphous? Basically just wash out all the energy barriers from site to site to site that your ion has to jump through. That's also what people do. So it's also a viable strategy. And that's what we'll talk about. So in terms of coating materials, right? People have looked at alumina, people have looked at lithium niobate that we talked about, and for chemical reasons. But we'll also talk about diffusivity reasons within these materials. But first, I'll revisit the discussion of the manganese dissolution problem, and also the instability of nickel at the thermal instability of nickel 2+, right? So in terms of decreasing the active material particle site, right, to increase to increase the rate capability, that's what people do. And so I've highlighted this one reference here, right, where it's a pretty complex geometry. And I say complex because it's core shell, so it's not complex like some weird, geometrical configuration, but complex as in the compositional control is complex. So within this nanostructure, the core is nickel rich. So you see that composition here. So the nickel 0.86. Okay. The nickel 0.86, and then the outer layer is actually manganese rich. And so one of the reasons why they decided to do that is so that the thermal stability of the outside layer is enhanced by having more manganese on the outside. Yeah. Although another important fact is so not only do you make the core shell, right, you change you make the composition complex, but also these are nanostructures. So, and they're anisotropic. So they're sort of like rods. And in their TEM, they show that the rods actually sort of mostly align. And so you can make this percolated network within the rod so that there's fast diffusion within that percolated network. So you can control anisotropy as well by having well-controlled chemistry and also well-controlled nanostructure. So that was, a really interesting paper. Now, can you scale this up? That's another question, right? That's always the question of, can you scale these very particular geometries? But this is a demonstration of how when you nanostructure a material, you can increase the diffusivity and control the percolated network so that there's fast ion diffusion along the direction that you want, while protecting the material chemically. And now, another really successful example is lithium iron phosphate. So this material has been studied, right, since the 90s, early 2000, well commercialized at this point. And if you look at the single crystal, you see that the fast ion transport direction in the single crystal is along the 010. That's the tunnel, you know, in and out of the board. Okay. But, and you could see that when you delithiate, when you look at the diffusivity, you can see that, you know, the delithiation is quite fast. It's under 0.01 second for a 100 nanometer structure, and less than a second if, you know, if the particle is moving to the micrometer regime. But that's not what you see when it comes to the bulk. The diffusivity is much smaller when it comes to the bulk material, and that actually should say 10 to the -10. It shouldn't be a repeat. That was a copy and paste typo. Okay. So what's interesting about this material is if the channels are blocked, and I will tap my message here. If the channels are blocked, because the ions are moving in and out in 1D, right? This is a well-known 1D tunnel structure. If they're moving in and out, if the channels get blocked because life, right? Because this is a real material, as in there could be anti-site defects. What does that mean? That means when you synthesize the material, an iron could just occupy, you know, a site where lithium, it could be in the tunnel where lithium could be. That's an anti-site. It's not where it should be, right? It's not at the site that it should be. Lithium could also be on an iron site. Iron could be on a vacancy. Lithium could be on a vacancy. So basically there could be all these defects that are just inherent in growing a material. And so if that's the case, lithium ions, right, they need a whole channel to move in and out. So they need the whole channel to diffuse. But if there's a blockage, now your fast ion channel is blocked. So the ion has to move to another site. That's a higher energy barrier. But if it's available, it will do it, statistically speaking. So if it can make that jump, it will, and it does. But it's going to come at a cost, right? It's higher energetically. So it's going to want to try to diffuse in the direction that it's the fastest and lowest energy barrier, which is the 010 direction. Okay, well, what does that have to do with decreasing the active material size? Well, if you make lithium iron phosphate smaller and smaller and smaller down to the 100, the 200, the 100, the 60 nanometer regime, what you get is at that concentration, how many sites do you have when you have a 60 nanometer particle? You don't have to answer that. That's actually a rhetorical question. I wasn't expecting anybody to do that, like the math in their head. But that's what you ask yourself. Statistically, if I have a smaller particle, I have smaller defect concentration because there aren't as many sites for the lithium ion for there to be even a defect. And in fact, it's less than, you know, a few, it's like 2 defect sites in like 16 nanometers. So that's all to say, if you decrease it, then you decrease the defect site, which means lithium ions can diffuse faster because there's not a lot of blockages. And so the paper I cited here, the Morgan and Cedar paper from 2004, the Malik and Cedar paper from 2010 as well. The 2004 is actually the table here. They worked it out from first principles, and they mapped out, you know, exactly as you decrease the particle size, you know, what are the percentages of defects that you're going to get, and that's how you increase ion diffusion as you decrease the particle, which means now your material can diffuse faster and thus operate at higher C rates. And so when people say, well, lithium iron phosphate is one of the few materials that can work at when nanostructured, that is why. Okay, so this is